Greetings, Gen Chem people. This is a re-recording of last night's help session. We ran the help session last night, but I didn't start the recorder at the beginning. We lost most of that wasn't recorded. So I'm redoing it this morning, Tuesday morning, and I'm going to post this recorded version online for those who weren't able to be here, or those who were here and want to look at it again. So what we're going to do is the first problem we're going to work through is homework problem number 5, or problem number 5 from the week 2 homework set. And then we did this one. This was the first problem we did last night, and then we started looking at and started going through the questions in the practice test. So this is where we'll start. And this is a constant volume calorimetry problem. Remember what calorimetry is. Calorimetry is the science of measuring the heat associated with different processes, like chemical reactions, for example. And in our lab last week, we ran calorimetry, and you saw me running it with a constant pressure calorimeter. And it was called a constant pressure calorimeter because it was open to the atmosphere. And the atmospheric pressure is relatively constant, so we call it a constant pressure calorimeter. This is a constant volume calorimeter, and it's somewhat different, and the calculations required for this kind of problem is a little bit different than what we did with the constant pressure. But let me describe what a constant volume calorimeter is so we can understand what constant volume calorimetry does. A constant volume calorimeter is a device, an instrument, that is actually just a steel box, a rigid steel box. But inside of that box, and I should state this right off the bat, that the box is insulated. It's covered, wrapped in insulation. And the purpose of the insulation is to do just that, to insulate whatever is inside of the calorimeter. So any heat produced inside of this box stays inside. Any heat outside of it can't get in. Any heat inside stays in. And therefore it's thermally separated from the surroundings. And we'll call whatever is in the calorimeter our system. So in a constant volume calorimeter problem or kind of device, the system is everything inside of that box, that insulated box. Now, inside the insulated box, what we have is a dish that has water in it. And in that water is something that we call a bomb. Now, it's not really a bomb like something that's going to explode. It is actually a steel-walled container. And in that steel-walled container, we put our sample. And there's our sample. And then we seal that container and we pump it. There's a little valve on it that we can add oxygen gas, and we pump it with a high pressure of oxygen gas, maybe 3-4 atmospheres pressure of oxygen gas. And then there is a thermometer that monitors the temperature inside of the calorimeter. And there's one more little piece. We have a wire that runs from the outside into the calorimeter and into that bomb. And that wire is connected to a little battery or some kind of device that when you push a button, it creates a little spark. So that's the calorimeter. And what kind of reactions do we run in here? What's the purpose, or what kind of heat energy are we trying to measure here? And typically, or often, is the heat energy associated with food products. And you know that whenever you buy a food product, there's a label on it that identifies its energy content, its calorie content. Like this one, you see the little arrows there. This tells us, this label says there's what, 120 calories of energy per serving. And you may wonder, where on earth do they get those calorie content, that energy content associated with the food product? Well, this is how they do it, using a constant volume calorimeter. So let's say that it was Life cereal, right? Life cereal, whose energy content we want to measure. We take a piece of that life cereal and we put it into the bomb. That's our sample in the bomb. And as we said before, we seal that. It's a steel wall container, and we pump it with a high pressure of oxygen. Now, the little piece of life cereal is actually a fuel. It will combust in the presence of oxygen. So when we have it in here with excess oxygen, a high pressure of oxygen, and we hit the little button on the battery that creates the spark, inside there, that reaction will take place, and the little piece of life cereal will be completely combusted and release its heat energy. So, and that heat energy that's released by the reaction will be absorbed by the water and by the inside walls of the calorimeter. But none of that heat energy gets out because the box, the calorimeter, is thermally insulated. So that's the idea. Now, in this particular problem, we want to determine, according to the problem number 5 on homework set number from week 2 homework set. We have a cereal, and we take a piece of that cereal, 0.425 grams, and we put it into the calorimeter. That's the mass of our sample, or cereal. And you're told that the calorimeter has a heat capacity associated with it that is equal to 5,000 joules per gram. Every calorimeter, constant volume calorimeter, would come with a little label or a manual that says this calorimeter has a heat capacity that we're representing as capital C with a subscript cal for calorimeter. Every calorimeter has an associated heat capacity, and that would be part of the, that would come with the instrument. Okay, so now we have that 0.425 grams of cereal in there. We've got everything hooked up. We close this up, and then we hit the little button on the battery. The spark takes place. That piece of cereal is completely combusted. Its heat energy is released, and we get a temperature change inside, because as the energy is released by the reaction, it's absorbed by the water and everything else inside of the calorimeter, and the temperature goes up. And you're told that the temperature change is equal to 2.25 degrees C. The temperature went up by that magnitude, delta T. Now, what you're asked to provide for this problem, and you have all the information available to do so, is to, 1, determine the heat energy of the reaction per gram of the cereal. Well, let's do that. The way you would do that is the following. We have Q of the system is going to be equal to, excuse me, Q of the system is going to be equal to 0. Now, why is that? Well, remember, the system is everything that's inside the calorimeter, but that calorimeter, the insides are completely thermally insulated from the outside. And recall what the heat energy is telling us. Heat, or Q, is the amount of energy exchanged as heat between the system and the surroundings. But we have it thermally insulated, so no heat energy is escaping the system, no heat energy comes in from the outside. Therefore, the change in the heat of the system, the inside of the calorimeter, is 0. But even though the Q of the system is 0, the heat energy exchange between the system and the surroundings is 0. There's a lot of heat energy exchange taking place within the calorimeter. The reaction is releasing heat energy as that little piece of cereal combusts. And that heat energy released by the reaction is absorbed by the insides of the calorimeter, by the water in the calorimeter, the walls of the calorimeter, the thermometer, and everything else inside. But we know that the sum of these heat energy exchanges have to be equal to 0, because again, we're thermally insulated, no heat energy exchange with the system. Now it turns out that, now we can solve for Q of the reaction. That's what we're interested in. right? We want to know how much heat energy is associated with the combustion of the cereal. So we can solve for that now. And Q of the reaction is going to be equal to negative Q of the calorimeter. We just solve this little equation for Q of the reaction. And don't drop the negative sign. So this is telling us that all of the heat energy produced by the reaction is completely absorbed by the insides of the calorimeter. And it turns out that the Q of the calorimeter will always be equal to the heat capacity of the calorimeter times the temperature change that occurred inside the calorimeter. Don't drop that negative sign. And now we know what the heat capacity of the calorimeter is. It's 5,000 joules per gram. And we know what the temperature change is. We multiply that to 0.25 degrees C. And what do we get? We get negative 11,250 joules. And that is the magnitude of heat energy given up by the reaction, associated with the reaction. But that's not what we're asked for in point A. In part A, we're asked to give the heat of the reaction per gram of cereal. So to get Q of the reaction per gram, we just take our negative 11,250 joules and we divide that by the mass of the cereal that was in our that we put into our calorimeter, and that was 0.425 degrees C. Oh, excuse me, grams. And what do we get? We get 25,000 joules per gram. Okay. And that is part A. Now you're also asked to provide a part B answer. And part B is, oh, by the way, notice that this is positive. We dropped that negative sign purposely, or you could think of us just using the absolute value of the result. And so there's 25,000 joules of heat energy given up for every gram of that cereal when it's combusted in the presence of oxygen. Now, part B, what we're asked to provide is the number of the calories per serving. We want that. Now calories is a unit of energy. Joule is an energy unit, and calories is a energy unit. We typically use calories when we talk about the energy associated with food products. So we're going to need to change joules in our answer from part A into calories, and we need to convert grams into quantity of serving. And the information for doing that is in the problem. It turns out that there are 4,180 joules per food calorie. And it turns out that there are 30 grams per serving. So we'll use these units, these unit relationships, to take our 25,000 joules per gram and convert it into calories per serving. So we have 25,000 joules per gram, and we're going to convert the joules into calories. So we'll use this conversion unit, and that means that there is 1 calorie for every 4,180 joules. And notice that our Joules will cancel. And now we have our energy expressed in terms of calories, CAL. And now one last change, we'll convert our grams into servings. And we'll use this conversion unit. There are 30 grams per serving according to this particular cereal. So we'll say there's 1 gram, excuse me, not 1 gram, but 30 grams. 30 grams per serving. And notice that now the grams cancel as well. And what are we left with? We're left with calories per serving. And you multiply 25,000 by 1 over 40, 4,180, multiply that by 30 grams per serving, and you get 179 calories per serving. And that would be the answer for part B. This was the answer for part A. There are 25,000 joules of heat energy released for every 1 gram of the cereal combusted. And part B, there are 179 calories, food calories per serving of that particular cereal. And that's the story. Now, notice that this calorie, CAL, should be uppercase. There are 2 kinds of calories, which make it confusing. There's lowercase calorie, which is an energy unit, and then there's another one, uppercase calorie. This uppercase C calorie is called a food calorie. And that's what we have in food products. The calorie content is actually in, the energy content is expressed in food calories. And it turns out that there are 1,000 little calories for every 1 food calorie. But anyway, that's not something you'd be expected to have to provide on the exam. But the calculations that we've done here, the understanding of constant volume calorimetry would. Okay. So that is that. Okay, so we worked our way through that problem number 5 from week 2 homework set, that thermochemistry problem on constant volume calorimetry. And now we'll start working our way through the practice test problems. And if you come to the help session tonight, there's going to be another one of these Zoom help sessions at 7 o'clock tonight. You should bring your practice test with you because we'll be making our way through that. Not that this is the only thing that we'll do tonight or that we can do. If you have questions about other aspects of what we've done in class or what is in the homework sets, other homework sets, please say so. We'll go through those as well. But we'll start by going through the practice test. So we're going to start with question number 1 on the practice test. And go. So question number 1 says we have concentrated hydrochloric acid that has a molarity of 12.1. 12.1 moles per liter of solution. And they want to know what volume of concentrated hydrochloric acid would be required to prepare 1 liter of 1 molar hydrochloric acid. So essentially what they're saying is we have this container and it has 12.1 molar HCl. Now that's not what we want. I mean, 12.1 molar HCl is much too strong a concentration to use in almost any experiment. So why do we have it around? Well, we have it because we use it as a stock solution. We talked about this in one of our online videos. Stock solutions are highly concentrated, accurate concentrations of different substances that we use to dilute to make solutions of lower concentration for real-world applications. So this is what we have. We have this stock solution of 12.1 molar. What we need, or what we want, is 1.0 liter of 1.0 molar HCl. So we're going to do a dilution. We're going to take this stock solution, take a certain portion, quantity, a volume of it, and dilute it up to 1 liter, such that we end up with that 1 liter having a concentration of 1 mole per liter. So how do we know what volume of this to use to do that? Well, this is the equation to use for any dilution problem. And that is the molarity of the stock times the volume of the stock solution will always be equal to the molarity of the sample you're wanting to create times the volume of that sample you're wanting to create. And notice, remember that this is molarity is mole per liter, volume is liter, and molarity, mole per liter on the sample side times liter. And notice that the liters cancel on both sides. And what this is telling us is that the number of moles that you get from this stock solution, the number of moles are not going to change because you dilute it. So the moles that you start with from the stock solution have to be equal to the moles that you end up with in the sample, because diluting it, just adding water, is not going to change the number of moles of HCl. And that's why this equation works. But this is your go-to equation. MV is equal to MV. Now it's just a matter of rearranging this equation. We're asked what volume of that HCl solution is going to be required. So we solve for that. The volume of the stock is going to be equal to the molarity of the sample times the volume of the sample divided by the molarity of the stock solution. And so now it's just plug and chug. So the molarity, or the volume of our stock, volume of the stock solution is going to be equal to the molarity of the sample, which is 1.0 molar, right? That's what we want, times the volume of the sample, which is going to be 1.0 liter, divided by the molarity of the stock, which is 12.1 molar. And notice that the moles, the molarities cancel. And what we're left with is liters. And we get 0.8, excuse me, that's not right. We get 0.083 liters. And that's the volume that's going to be required. Now, typically they would convert that volume into milliliters, and you know that 0.083 liters, there's 1,000 milliliters per liter. So multiplying through there cancels our liters, and we get an answer of 8.3 milliliters. So the way to create a 1 liter volume of 1 molar HCl, you go into the stockroom, you find your 12.1 molar stock solution of HCl, and you take out 88.3 mils of that, and you dilute it up to a volume of 1 liter, and you'll have your 1 liter of 1 molar HCl. And that's that story. And that's as far as we got last night. Hopefully things will go smoother and faster and more efficiently than in tonight, Tuesday night, in our help session at 7 o'clock tonight. than they did on last night. Last night was the first time I ever did anything like that, and had a few little goof ups, but this is the story. And again, if you come tonight, bring your practice test with you, because we'll be going through that and working our way through the problems. And if you're here, then you can interrupt at any time when I'm doing these calculations. If something doesn't seem to be adding up, or if you can't see or can't read or can't hear what I'm saying or doing, we can address that. But that's it for now.